Hello, it's Dr. Jovanelly. I'm excited to be here with you today, studying structural geology, one of my favorite aspects of geology for sure. Just to review where we've been, we have talked a little bit about plate tectonics, which leads into structural geology. So the idea that the earth is formed by plates and those plates have movement, an idea that was initially introduced by Alfred Wegener, the German meteorologist who really spent his whole life trying to convince people that the plates were moving. He provided different lines of evidence to suggest that there was once a supercontinent. That supercontinent is also called Pangaea, and Pangaea can be separated into two parts, Laurasia and Gondwanaland. Laurasia is the continents that stay north of the equator, and Gondwanaland are those that remain south, with the exception, of course, of India. So the idea of plate tectonics became a theory in 1965, thanks to the studies done by Henry Hess, Murray Tharp, and Vine and Matthews. The Wilson cycle describes the theory of plate tectonics, showing that there is divergent plate boundaries, and those divergent plate boundaries meet convergent plate boundaries that force the continents into Pangaea. And then that cycle happens every 500 million years, where you're developing a supercontinent, and then they pause, and then they break apart. So over the course of 4.6 billion years, there's been about 9.5 Pangaea cycles. So we're halfway through our next supercontinent, or we're on our way to our next supercontinent in just 250 billion more years. So I introduced plate tectonics before structural geology because structural geology really describes what's happening in the lithosphere. So remember, the lithosphere is the crust, both oceanic and continental, and the upper mantle. So the rigid parts of the earth are described by structural geology. When we talk about structural geology, we often use this stress and strain diagram. So you see that strain is on the x-axis, and then stress is on the y-axis. And we're going to define those. Go ahead and write this diagram down in your notes. You're going to see it on your exam for sure. You're probably going to have to fill it in. So just take a minute and write down this diagram. The stress is on the x, the strain is on the x, the stress is on the y. And then you see a curve that describes elastic behavior. The elastic behavior ends at the elastic limit. When we move into plastic behavior, and then plastic behavior ends at brittle failure. We're going to describe each of these components after you get it in your notes. Are you ready? Yeah, me too. Okay, so let's start by describing the y-axis, stress. A rock's structure will result from its response to stress and strain. Okay, we know that. And so when we talk about stress, we are describing it in pounds per square inch. And when we identify different types of stress, we look back towards plate tectonics. So we can describe it as compressional stress, tensional stress, or shear stress. And so compressional stress will have to do with those convergent plate boundaries, where you have two systems that are moving towards each other. We can use the Nazca plate and the South American plate for the development of the Andes Mountains as an example. So there's compressional stress at that boundary. It's reported in pounds per square inch. We can see tensional stress, and of course we can describe Iceland as one of those places where you have divergent plate boundaries that are moving apart from one another at 2 centimeters per year, or 13 miles per million years. Talk about tensional stress, huh? Where it's pulling apart, and then you can have shear stress. And shear stress is lateral. So we'll describe the San Andreas fault as an example of that later in this lecture. So shear stress is a lateral right to left movement. So the big thing to know right now is that stress is reported in pounds per square inch. When we talk about strain, strain is going to result in a change of volume or shape or both when an object is undergoing stress. So strain is the percentage of change in cubic inches that you can visually see. Strain is often the result of adding stress. So these compressional, tensional, or shear stress is going to result in change in terms of cubic inches. So let's go ahead and tease out each of the components of this diagram. This lecture is a little heavy on definitions at first, so just bear with me. Okay, so the elastic portion of the diagram is when you're adding low amounts of stress and low amounts of strain. And when we describe the elastic behavior, that means that a deformed object recovers to its original shape after stress is reduced. So you're adding, you're taking getting ready to take your exam, you're studying, you're stressed, and then you take the test and you're completely fine because you got an A on it, right? So same thing here. We're thinking in terms of stress being added to a rock, maybe in terms of an earthquake or any of these stresses, but it's in such low amounts that nothing changes. The appearance of the rock does not change until you reach something that's called the elastic limit. So if stress and strain are applied continuously for a long period of time at a certain amount, then the rocks are going to deform. But you have to reach the elastic limit in order for this to result. So after you've exceeded the elastic limit, you are going to be in the portion of the diagram that's called plastic behavior or ductile behavior. Those words are synonymous. By definition, deformed object will bend under stress and does not return to its original shape after stress is reduced. So the kicker is so rocks before the elastic limit are going to be unchanged. After the elastic limit, they are going to have enough stress and strain where they change shape, even after the stress and strain is reduced. And this plastic behavior is the mechanism that we use to describe when rocks are folded. And so you maybe have seen or noticed examples within the Appalachian Mountains or somewhere else where rocks are bent. So what we know by the principle of stratigraphy is that the laws of stratigraphy is that rocks are originally horizontal, so they're originally flat. And so in order for them to be bent, something must happen in their natural environment to cause them to change shape. And so without knowing anything else, when you're looking at these pictures of these folds, these are called folds, that they have exceeded their elastic limit and have changed permanently. When we describe folds, we talk about a right limb and a left limb, and you look to see the center of the axis. So the axis is called the point of inflection, or the point at which the bend occurs. And sometimes they're symmetrical and sometimes they're asymmetrical. So the picture on the right is a symmetrical axis to the fold, and then the one on the lower left is asymmetrical. So next is describing what happens after you meet the plastic limit. And after you meet the plastic limit, rocks are going to behave brittly. So by definition, an object under high stress will fracture. This is the mechanism by which faults form in rocks. So you might have heard of faults or fault lines, with the San Andreas fault, right? Rocks at or near the Earth's surface will deform by mechanisms as temperatures and pressure are low. So in this case, you have a high amount of stress and strain on a rock, and it will cause it to break. So it's going to cause it to cause something that's called a fault, and that essentially when rocks behave brittly. So there's so much stress and strain that they just collapse on themselves. They break. And of course, closer to the the Earth's surface, the rocks are going to be more brittle because they're under less temperature. So this picture is an example of a fault. And so now what I want to do, that we have an understanding of elastic behavior, plastic behavior, and brittle behavior, is I want to describe these a little bit more, specifically brittle behavior. So, and again, heavy on definitions, but we need to first describe what a fault is and then the components of a fault. So these are all geologic structures, right? And by definition, a fault is a fracture in the bedrock along which movement has taken place. Brittle deformation occurs quickly. So a fault is where movement has taken place. And we can have different types of faults, but that's kind of, the fault line is the source of movement, also the source of earthquakes, which we'll talk about later. Faults are described by identifying two things, the hanging wall and the footwall. And so we can look at this diagram here, and we can identify the footwall on the right and the hanging wall on the left. So the fault line is in the center of those things, and when you're looking at a diagram like this, you need to identify the footwall and the hanging wall because you need to identify the type of fault, and it's going to be the position of those. So a footwall, underlying surface of an inclined fault plane, surface you can walk on. So what you're imagining is that your footwall is always going to be underneath your feet, and you're imagining a person walking up or down the footwall. So the footwall has to be something that you can put your feet on, and then the hanging wall is the overlying surface. So these are terms that coal miners often use. The footwall you can walk on, the hanging wall is where you hang your lantern. So the hanging wall is adjacent to the footwall. Seems that the screen is a little off kiltered, but we can work through it. So what I'm showing you here is an example of a normal fault. Now, by definition, the hanging wall block moves down relative to the footwall. So on this diagram here of this normal fault, I'm asking you, is the footwall on the right or the left? So it's a place that you could plant your feet if you're walking up. And so in this case, the footwall is on the left and the hanging wall is on the right. So the footwall is the portion over to the left of the screen and the hanging wall is over on the right. When we describe normal faults, we often talk about them being a tensional fault. So a fault that is being pulled away, also known as a divergent plate boundary. And so you can imagine, I don't know, having gum or silly putty and you pull it apart, the low-lying area is going to sink or subside, and that's what's happening in this case. So when you have these divergent plate boundaries, the hanging wall is going to fall relative to the footwall, and that is the definition. When we talk about large-scale features related to normal faults, we often call them Horst and Graben features. So the Graben would be in this diagram here, the Graben would be the hanging wall and the Horst would be the footwall. So Horst and Graben features, and really they're like valleys. So the Graben is a low-lying feature, often getting infilled with a lake or an ocean, and then your high elevation or ridges are often called your Horst. So here's another example of a hanging wall and a footwall. So you can see the picture of the person, and they're standing on the footwall, and then the hanging wall is above them. The fault is the area that's in between. And so when you're looking at these diagrams, especially real images like this, which you'll identify for one of your exams, you're trying to imagine where the land was together and then how they've moved. So you're looking to line up these different pieces of stratigraphy to think about, well, where were they connected and then how did they move? I think you can see this picture. Here is another example of a normal fault. And so I give you the line to show you where the fault is. And then the question becomes, is the hanging wall to the right or to the left? These are all normal faults. So in this instance, the footwall is on the left and the hanging wall is on the right. Hanging wall block moves downward relative to the footwall. And then I just want to give you an example of what a horst and graben might look like. So your hanging wall blocks are your grabens, and then your footwalls are your horst. So it's the difference between high elevation and low elevation. This is a real image of a horst and graben. So if you ever have the chance to drive out west and you go through the great state of Nebraska and into Colorado, and you're in eastern Colorado, you're going to go through the ancestral Rockies, so or the foothills of the Rocky Mountains, and so that's also called an area that's called the Great Basin. And so you're going to go drive up and down drastically into these horst and graben type of features that's representing by the interior of the United States being pulled apart at modern day, and that's why there's seismicity and earthquakes. This is just an aerial view of a horst and graben feature. So you've got horst, and then you got your graben in the center. And there's one more diagram or picture. So horst, graben, etc. Okay, so we have normal fault, and then we have reverse faults. And in a reverse fault, the hanging wall block will move up relative to the footwall. So normal faults, the hanging wall block moves down. Reverse fault, the hanging wall block moves up. And so that's why it's so important to identify which one is the footwall. And in this example, the footwall will be on the right, and the hanging wall block will be on the left. And this is a reverse fault. And oftentimes when we talk about reverse faults, we're interested in convergent plate boundaries or compressive forces. So you're imagining pushing a carpet together and you end up with a ridge. And that would be an example of like a hanging wall block moving its way up to the surface. So you're adding tension and stress, something has to give, and usually something will move up. And that would be the hanging wall in this example. So we can practice with a few of these. In this example here, again, you have to look for where the stratigraphy lines up, so where they're matching, and then ask the question, well, what's the footwall? And then you ask, is the hanging wall block moving up or down? So in this case, the footwall is on the left, and the hanging wall block is on the right. In this case, again, we have to ask and identify where is the footwall. So the footwall is on the right, on the bottom, and the hanging wall block is moving up relative to the footwall. In the center here is the fault line. And so the footwall is on the right, and the hanging wall block is on the left. And one more. This is showing you a building, because buildings often move too. And here we see the footwall on the left and the hanging wall block moving up relative to the footwall on the right. And same thing with this. So you're looking to see where the stratigraphy meets itself and asking the question, which is the footwall and which is the hanging wall. This is really outside the scope of Geology 101, but for those of you who will be taking geomorphology with me, Geo 360, geomorphology explains Earth system processes, mountain building, etc. Just note that when you have a reverse fault that is at an angle of 30 degrees, it's then called a thrust fault. So it's still a reverse fault, but the slant dip of the fault is going to be less than 30 degrees. And that's what we're seeing in this picture. If I were to give you this on an exam to identify and you called it a reverse fault, that would be fine, because it is. Okay, so we talked about normal faults and reverse faults. Our next thing is identifying lateral faults. So we talked about shear stress. That's what a strike-slip fault is. Strike-slip fault is also called a transform fault. So those words are used synonymous: strike-slip fault, transform fault. I think your lab manual might use the word transform, so write that down. By definition, a fault where the movement or slip is predominantly horizontal and parallel to the strike of the fault. So in normal reverse faults, we were worried about what that hanging wall block was doing, whether it was moving up, reverse, or down for normal. In this case, we're looking for lateral movement instead of, or horizontal movement instead of vertical movement. So your slips are either going to be right lateral or left lateral, but identifying that is really outside the scope of Geology 101. We're just looking at the general idea as to, is it a normal fault, reverse fault, or a strike-slip fault? And so one common example of that is going to be the San Andreas fault. And so it's really neat if you look in Google Earth, you might want to do this after this lecture, because you can see aerial examples of where the San Andreas fault actually is, because it significantly disrupts the topography. And we talked a little bit about the idea of elastic limit, so putting pressure on something and a rock type and it rebounds, you don't see anything. But once that elastic limit is exceeded, you start to see rocks behave plastically. And so that's what you're seeing in this diagram here. The rocks are, the train track is being ductily bent at the Earth's surface, so it's no longer a straight line. And so that's an example. Oftentimes, as a precursor to a major earthquake, you can see these small scale changes in the landscape. The railroad is a bigger example, but built up over time. And so looking at the rows of crops and seeing them slowly moving and behaving plastically means eventually that they're going to arrive at brittle failure. And so a big strike slip will happen, as in this picture, where you see this river system, and the river was once together, right? So the river was once flowing together in one direction, and then you get a major disturbance. Sometimes it's going to be more than a mile that happens at one time. So now when we look at the plate tectonic diagram, it should make a lot more sense. So we've already identified the convergent plate boundaries are the sawtooth. The divergent plate boundaries are the bars. The big arrows represents overall direction of movement. And so now you can have an idea of where you would expect to find these different types of fault conditions. So if you look at the Nazca plate and the South American plate, it's a compressional convergent plate boundary. So you'd expect to see reverse faults. In Iceland, where you have tensional forces, a divergent plate boundary, you'd expect to see normal faults. That's right. And over here on our eastern or western seaboard, where you have the North American plate against the Pacific plate, what you'll notice now is that the North American plate is moving to the west, but the Pacific plate is moving to the northwest. So although you do have some components of a convergent plate boundary, truly what's happening is the Pacific plate is moving across the North American plate, and so it's shearing, and so that's how you end up with the San Andreas Fault. And so it's projected that there will likely be some major earthquakes by 2030 if we're keeping in track of those recurrence intervals and frequencies that we've talked about in previous lectures. So in this case, it's easy enough to identify that this is a left lateral fault, and it's because the Pacific plate is really the dominant motion that's causing the shearing effect. And so when we look at and begin to talk about earthquakes in California, earthquakes happen all the time because there's always that small amounts of stress and strain that are built up. So you get low energy earthquakes like a magnitude 2, a magnitude 3. But eventually it's predicted that there will be a major large magnitude event to shear places in California. It's expected to be quite drastic. So we talked about faults, and that leaves us to talk a little bit about folds. What we said was that folds are the result of plastic behavior or ductile behavior. And when you have a fold that is upward, that is called an anticline. So you can think of like a anticline, and that's where the arch is upward. And I mentioned before that when we talk about the center of that line is called the axis, and then you have the right and left limb. So right and left limb of the fold. And we can see anticlines that form these rocks. So remembering again that they were initially flat, and then you have had compressional forces to cause them to bend slowly over time. They didn't break, they did not exceed brittle failure, likely, but there was enough stress and strain to bend them. So these are all anticlines, where you see the A shape. This is an asymmetrical anticline because the axis is not in the center, or plunging anticline. And then anticlines, and then you can also have synclines. And so a syncline is when you form a U shape. Still, you can identify the center of the fold. These are different types of synclines. So we introduce anticlines A-shape and synclines as U-shape, knowing that like in a big ridge and valley complex, you can have both. So you could have a ridge, like Lavender Mountain, be an anticline, and then a valley, like Big Texas Valley behind it, be a syncline. And one of the ways that we describe that using a geologic map is looking at the ages of the rock. So when we look at a dome, which represents an anticline, dome and anticline are synonymous, we think about those rocks being formed originally horizontal and then bending, right? So when you look at the stratigraphy of that bend, your oldest layer is on the bottom and your youngest layer is on the top. And so if you cut off the top to look down in map view, the oldest layer is going to be in the center. So if you're looking at the bullseye there, the gray is the oldest layer, and then it gets consecutively younger away from it. So on a geologic map, that's one way that we identify it, because we don't necessarily have a cross-sectional view. You can't look at depth. You can only look at the ages of the rocks from the surface. And then oppositely, when we look to identify a basin, we will look at the age of the rocks again, and they're layered oldest to youngest. But this time, when you look at it in map view, so essentially you're cutting off the top of the U shape, you see the youngest layer in the center. and then it's going to get consecutively older. So the dark yellow in the center, the gold color that has the speckles, that is going to be younger than the yellow, than the gray that's beside it. And we're going to play around with some of these when we get to class. And this is one way that we know that the great state of Michigan is a basin, and it is the result of a lot of ice that formed on top of it, ice and erosion. And one of the questions might be, why do we care about faults and folds? And one of the reasons why we care is because those faults and folds act as trap for oil and gas. So when we, if you're a petroleum geologist, which is a whole section of geology, their goal is to identify where the oil and gas is. They often start with looking at faults, and that's because oil and gas are going to migrate up to the top of that fault, and the fault is going to act as a trap. So it's trapping the movement of oil and gas. And then you also look for anticlines and often drill at the very top of the anticline to find the oil and gas reserves. And we're going to play around with that a little bit in class when we meet this week. And I think I'll stop here for today. So I'm glad you learned a little bit about structural geology, specifically looking at elastic, plastic, and brittle behavior, and how convergent and divergent forces can create either normal faults or reverse faults, and then how rocks can behave plastically and turn into folds. So hopefully you can use those now to interpret the environment around you as you travel.